Welcome to Bankable. I'm Doreen Abisundra, your host and a proponent of innovative technology and financing solutions for AI infrastructure, decarbonization, and energy security. This is the first Bankable podcast to showcase nuclear fusion. Why the interest? Well, the IAEA, the International Atomic Energy Agency, describes fusion as a technology which can generate 4 times more energy per kilogram of fuel than fission and nearly 4 million times more energy than burning oil or coal. Our guest today explains fusion and how it differs to fission, plus gives us an insight into the UK's Spherical Tokamak for Energy Production Programme, STEP, and how fusion could be the long play for addressing energy poverty, enabling AI advancement, and energy security and decarbonization. This conversation was recorded just a few days before STEP was awarded £2.5 billion in the UK's June 11th spending review. Notably in this chat, we learned that there are between 10 to 20 commercial developers which have raised between $5 to $10 billion to date. Hence, there is indeed private investment appetite for fusion and an opportunity for non-government entities to invest across the fusion energy supply chain. Enjoy the conversation. Today we are joined by Joe Milnes from the UKAEA. Joe, I'm particularly excited to hear what you're doing, who you are, in particular, what technology you're working on, and really grateful for the time that you have with us here on Bankable.
No problem. Thank you very much for having me.
So let's start with the very first question, Joe. Tell us a little bit about who you are and what has brought you to the current position that you have right now.
Sure. So, my name's Joe Milnes. I'm a mechanical engineer. I grew up in Oxford and realised early on I had a big interest in the sciences, in particular physics and maths, and also like the idea of building things. So I decided to go to university and do a degree in mechanical engineering. And I got interested in my current field of fusion because there is the UK's fusion laboratory is in Oxfordshire, 10 miles away from where I grew up, and I did a work placement here and loved it, was hooked. So once I'd finished my degree, I applied to get onto the graduate program and have been working in fusion ever since.
That's such an incredible story, Joe. So literally, your career was in your backyard growing up, effectively.
Yeah.
Wow. So tell us a little bit about this company that you work for. What exactly is its business? What does it do? What is its product or its service? And obviously, I hear fusion, but so put it into a bit of a layperson's explanation, please.
Sure. So I work for the UK Atomic Energy Authority. This is a government body. So I'm a public servant, like my other colleagues here, the other physicists and engineers I work with. So at the UK Atomic Energy Authority, we do research into a process called nuclear fusion. So this is the process that powers the sun and the stars, where if you get gases hot enough, you can get them small elements to fuse together to create heavier elements, and that releases a huge amount of energy. And so, that gives us the heat and light from the sun. And if we can build machines on Earth to recreate that process, we should be able to harness that energy to power the world sustainably with no carbon. So it's the ultimate energy source. Most countries in the world have a fusion program. I think it's fair to say the UK leads the world, is one of the world leaders in fusion. And I've been doing that for 25 years, ever since I started here as a young engineering graduate.
Incredible. And I notice you're in your office, so to say. Tell us a little bit about what we're seeing in that background.
Yeah, so today I'm coming to you from the control room of one of our fusion experiments here at the laboratory. So behind me is the control room for a machine called Mast Upgrade. It's yeah, it's a device called a tokamak, which is where you build a sort of a metal donut, as it were. Sort of the mast is about 4 meters diameter by 4 meters tall. You inject your fuels that you want to fuse into that metal donut, and then using very high currents and heating systems and strong magnets to suspend that fuel away from the wall, you can try and get to the conditions needed for the particles to fuse and produce that energy. And so every 20 minutes or so behind me, they'll be running a fusion pulse and actually reproducing the process that goes on in the sun. So yeah, it's quite a nice place to hang out in and get to see all the cool stuff that my colleagues do on a daily basis.
Incredible. And you mentioned fuels. So this is still within that question about what exactly the UKAEA is. So tell us a little bit more about what you mean by fuels. When you talk about the high temperature, tell us a little bit more about that technology and exactly what it is that is actually generating the electricity or the power or the ultimate product that it comes out from from the fusion process.
Yeah, so to go into a bit more detail about how the fusion process works, I mean, in theory, you can fuse any particles if you get them hot enough, but the easiest fuels to fuse is hydrogen or hydrogen isotopes specifically. So there is a naturally occurring isotope of hydrogen called deuterium that you can get from seawater, and then there's another hydrogen isotope called tritium, which you can breed from lithium. So deuterium and tritium are the easiest fuels to fuse, and I use that term loosely because when I say it's easy, in the machine behind me, we have to get those fuels up to between 10 million and 100 million degrees Celsius, so 10 times hotter than the center of the sun to get the fuels to fuse. So it's quite an undertaking. We know how to do it. We do fusion every day here, but the trick is to do that process in an efficient way so that the amount of heat you then generate from the fusion reaction is far greater than the heat you put in to get the reaction to start. If you can do that, you've got net energy gain, and then you can use that net energy to effectively boil water, to turn water into steam, to turn turbines, and then eventually put electricity on the grid. So that's what we do here. We spend all day, every day, trying to perfect that process with a view that sometime soon we'll be able to design the first prototype power plants where we actually put fusion power on the electricity grid.
And you mentioned words such as tokamak and getting the energy to be so hot. Can you tell us exactly a little bit more about tokamak?
Sure.
What it is with it, if there are other fusion processes or other words that we should associate with fusion other than tokamak? And secondly, how do you get to those 100+ degrees Celsius that you were talking about?
Sure. So there are a number of ways you can try and achieve these very, very high temperatures, these very difficult conditions to get fusion to occur. We're focused on the Tokamak concept, which comes from a Russian acronym, but it basically means a toroidal vessel surrounded by magnetic coils. So what we do is we put a small amount of fuel inside a toroidal, a donut-shaped vessel surrounded by magnets to keep the fuel away from the walls. And there are three ways that we heat those fuels up to the temperatures required. One is we pass a current, several million amps, spinning round inside the donut vessel, and that'll get you pretty hot, up into sort of 1,000,000 degrees or so. But to get right to the 10 million or even 100 million degrees, you need other heating systems, and there are two main ways we know how to do that. One is to fire beams of particles in through a port through the side of the vessel. So we just accelerate particles and fire them in through a port, and they exchange their kinetic energy and heat up the fuels, which has now become a plasma. We heat up the plasma even more. And the second way is by firing in electromagnetic waves, RF waves. So a bit like the way your microwave works in your kitchen, where you fire in electromagnetic waves that resonate at the temperature of the water molecules, and the water molecules start to jiggle and heat up the food. We do the same thing in a tokamak. We fire in electromagnetic waves that are at a particular frequency that excite the particles, the ions and the electrons that are in the plasma, have a sort of a rotational frequency, and if we can fire in waves at that frequency, they speed up and they get hotter and hotter. So through current, beams of particles, and electromagnetic waves, we know how to get these fuels up to the very, very high temperatures that we need for fusion to occur.
Incredible. And how would you see that difference between fusion and what we often tend to see when we discuss nuclear being fission? Effectively, what is the key difference technically between them, and why do we even need fusion if we already have fission?
It's a great question. The difference between fission and fusion, quite simply, is that fission is large atoms like uranium splitting apart, and that releases a lot of energy. Fusion is usually smaller atoms fusing together, joining together to make heavier. So that's the fundamental difference. One is splitting, and the other is joining or fusing. So yeah, all current nuclear power stations that provide power to the grid are fission power stations of various designs. They are carbon free, they are base load, so they provide energy without the sun shining or the wind blowing. You know, I'm a big fan of fission. I think they are very important to the energy mix. There are potential downsides with fission, which is the splitting apart process actually happens quite, I say easily, but you know, if you have to control that splitting apart process quite carefully, because if you don't, you can get you know, runaway reactions and overheating, which can cause dangerous events. So you have to control it quite carefully. There is also a waste challenge. Some of the waste that comes out of fission power stations needs storing for quite a long time. There isn't much of it, but you do need to store it. So like any energy source, it's not perfect. As I say, I personally believe we need it. We should continue to use it. But then you ask, well, why do you need fusion? Fusion offers the promise of having thousands, if not millions of years worth of fuel. So there's a lot of fuel out there. We're never going to run out of fuel. It also is intrinsically safe. So unlike fission, fusion is very, very hard to do. So that means at the moment we can't actually produce electricity from it. We are confident we will do one day, but it does mean if there's ever a problem with the reactor, because it's so hard to do, if anything goes wrong, it just stops. It can't run away. So fusion is intrinsically safe. We also think if you select the materials carefully for a fusion reactor, the amount of the amount of time that materials stay radioactive is significantly reduced. So if we pick our materials carefully, you might be able to design, build, and run a fusion reactor, and then when you're finished with that, you might just need to store the materials for a few hundred years, and your grandkids or your great grandkids can dig the stuff up and recycle it. Whereas for most fission reactors, the amount of time that the waste stays radioactive is far, far longer. So there are a few reasons it's worth going for fusion. But the biggest challenge at the moment is we can't get more power out than we put in for a sustained period. We think we know how to do that, and we're designing the first generation of prototypes that should do that. But we're not there yet. So we keep needing to work very hard on this project.
Got it. And in our preparation for our conversation, Joe, you were talking about various different laboratories across different countries and regions that are all looking to engage in this creation of a fusion process. Maybe talk us through a little bit about that. You did mention that the UK is leading the drive in fusion energy. Give us that global perspective of what we can expect in the development of the fusion.
Yeah, sure. So it is, fusion truly is a global effort. You know, as I said earlier, most countries have fusion programs, historically generally funded, publicly funded, but more and more in the last decade, more private money has been going into private fusion companies. But there's a big program in the US. China has a big program, as does Japan, Korea, most European countries, and the European program, as you'd expect, is quite coordinated. The UK, India, Canada, they all have fusion programs to a certain degree, and more and more it's a mix of publicly funded government labs like the one I work in, along with more private fusion companies who are trying out their new ideas and hope to be one of the first to crack it and develop the kind of IP and designs that they can then sell and license around the world to pay back to pay their investors back. So it's a very exciting time in fusion. In my whole career I've not seen the level of interest and the level of funding that's going into fusion, and it's difficult. It's going to be difficult to crack this. So the more different ideas we've got, the more players all trying to do this, the more chance we have that one or two will really break through and demonstrate that we can do this economically and actually build fusion power plants that will produce electricity that are at a cost that people are willing to buy. So we're confident the UK is very well positioned to be one of the successful players, but there are lots of players and lots of people catching up. So we've got to stay at the forefront in this field.
Excellent. That's a perfect segue to the next question, which was to talk a little bit about, obviously within how much you can say, about the so-called financing journey that the UKAEA has been on, and perhaps a little bit about your current or future financing needs.
Sure. So the organization I work for, the UKAEA, is fully publicly funded. It's funded by the taxpayer. So we are sponsored by the Department for Energy Security and Net Zero, and we propose a research program to them, and depending on how successful we are, we get awarded a budget each year to try and progress, to make the progress we need to make in fusion. So we are fully publicly funded. There are 10 to 20 companies around the world that have raised, I don't know the exact numbers these days, but somewhere between 5 and 10 billion of private investment over the last sort of decade, spread, as I said, across about 10 to 20 companies. And we are figuring out ways that we can work with them to take all the investment that the taxpayer has put into our knowledge and the progress that we've made, and how do we work with these new companies and new organizations to help them progress as fast as possible without giving away the IP in an uncontrolled manner. So we're just sort of on that journey as to how do we work with the private companies effectively. It's worth mentioning another project that we have kicked off, again publicly funded. It's a project called STEP. This will be the UK's first attempt to actually design and build a prototype power plant that will put electricity on the UK grid. It's a very exciting project, and that will involve both our laboratory. It will be led by a subsidiary to the laboratory called UK Industrial Fusion Solutions, UKIFS. Their sole goal is to deliver this STEP machine, and the way they will do that is by contracting the laboratory, us, UKAEA, as the fusion partner, and it will also bring in an engineering partner and a construction partner from industry, and they're going through a commercial process at the moment to identify those partners. So very soon the STEP program will be channeling a lot of the public funding that they receive into the UK and possibly global supply chain to help design and build the STEP machine. That is being set up in a way that if they make the kind of progress they hope to make, that it will be investable. So it's been set up in a way that once they get to a certain maturity, if private investors want to be involved in STEP, they will be able to invest into that project. At the moment, though, it's fully publicly funded. So that's kind of where we are on the finance piece.
Incredible. And perhaps give us an indication of where the UK is in comparison to another fusion project that we typically hear of called ITER, ITER for the audience. Tell us a little bit more about your interaction with ITER.
Yeah, so ITER is an incredibly important and global project. It's the first machine we think that will deliver industrial scale levels of fusion power 500 megawatts is the nominal target, which is substantial. It will still be an experiment, but it will be a real check as to whether fusion is a sort of a viable long-term energy source. So it's being built in the south of France, but it has so Europe is funding about 50% of the cost, and the remaining cost is being split across partners from across the globe, which includes the US, Russia, China, India, Korea, Japan, and apologies if I missed any. I think there's a total of 7 or 8 partners. So half the world's population is represented by the countries that are involved in ITER. It is an enormous project, one of the most challenging technical undertakings humanity's ever attempted. They've had some challenges because they're effectively the first project that's really trying to do this at scale. So they've had to build new supply chains that didn't exist before, had to overcome challenges that no projects have had to overcome. So they have had some challenges, and it is over budget and it is late. And obviously, a lot, we're very keen to, as a community, to support it so that it doesn't slip or go or become any more expensive. But it's an important project. The UK, before Brexit, when we were part of the EU, we were very much an active participant in the design and construction of ITER. Since Brexit, we have been trying to figure out a mutual arrangement that allows us to get back in to working with ITER, because again, we want to make that a success. We think we have a lot to offer, and I think ITER technically recognise that, but obviously it needs to be done in a way that the EU and the ITER Council are happy with. So at the moment, we're not formally part of ITER, and we're seeing whether there are ways to get back into that project. But regardless, it's a very important program that we will try and support wherever we can.
Thank you for that. And perhaps just stepping back and from a high level, how is it that what you're doing within the UKAEA, whether it's ITER or generally that entire development within fusion, how is it that fusion is contributing to either decarbonization, AI infrastructure advancement, or energy security, or all three for that matter?
Yeah, a great question. I mean, the short answer is it isn't yet. This is sort of high risk, high reward stuff. This fusion is one of the hardest things human beings have ever tried to crack. If we crack it, it will have an enormous impact on all of those things you've just mentioned. So we need to do everything we can right now with all the other technologies, renewables, conventional fission, sustainable housing, everything we can to reduce our carbon footprint and try and get as close as possible to the net zero targets that are being set. But we also need to play the long game, because energy consumption is only going up. We're lucky in the UK in that we're a small windy island. We can get quite a lot of our energy from renewables, but that's not true of all countries. So we think fusion is going to be essential for the sort of second half of this century, and then for the hundreds or thousands of years that go beyond, to keep providing carbon-free electricity. So fusion is the kind of the long play. Once we have it, then we'll effectively have almost limitless energy, carbon-free, that will be able to power the AI data centers of the future, not to mention bringing the whole world up, bringing them out of energy poverty and getting everyone to a living standard that they deserve. So it really is the holy grail when it comes to the long term, but it's not the case that fusion will make a significant dent to the net zero targets of the next sort of 10 to 20 years. We've got to do lots of other things to do that. You mentioned AI. There's quite a nice circular argument there. We're pretty confident that AI can have a major can really turbocharge our efforts to design and build the first fusion power plant. So we're investing heavily in AI and high performance computing to do the simulations that we need to design and build these power plants. So at the moment, we're a kind of a user of AI. If we deliver fusion, then we can sort of pay that back, and the fusion power can help power the AI data centers of the future. So there's a kind of a circular logic there. And in terms of energy security, what's great about fusion is that the fuels, deuterium and lithium, effectively that you can mine or get from seawater as well, are spread all over the world. There isn't really a kind of a Saudi Arabia of fusion fuels. Everybody has access to those, so it should be a major step forward in terms of countries being energy secure. If they can build fusion power plants, they should be able to access that fuels directly. So it really offers a huge amount. We've just got to get it over the line and get the first fusion power plants on the grid.
Mm-hmm. And thank you for picking up on that question about AI. That's a brilliant oversight into how AI is being used currently, but yet at the same time is going to be generating a solution for what you're doing as well. Isn't that correct?
That's right.
Incredible. Obviously, this is a podcast about financing and what makes this bankable. So what we're doing is trying to work out why the investors, whether it's debt or equity investors or perhaps some of the venture capital, people with venture capital money, should be looking at fusion. If you can give us in a nutshell why fusion is bankable for these investors and lenders, please.
Yeah, it's certainly the case that those sort of investors that you've just mentioned, those types of investors, are definitely getting more interested and putting money into fusion, albeit in a careful, sort of measured way. I mean, again, I don't have the numbers, but the world energy market is trillions and trillions. So, and there's no question that the world is going to have to go to carbon-free sources. So if you can invest in a technology or indeed an entire power plant design that can deliver fusion energy and just get even a small piece of that, the returns are astronomical. So the returns are huge in the long term. But the other thing we're very careful about, particularly in the UK and with the STEP project that I mentioned, is we are also looking at sort of adjacencies. So because of the very smart scientists and engineers that are working on designing fusion systems, we are also keeping an eye out as to how we can spin out some of those technologies to other markets. And I mentioned magnets before. We need very, very powerful magnets to run these Tokamak machines, and there's all sorts of research and development going into how powerful we can make those. And there are examples out there of companies who both have a fusion arm and design magnets for fusion, but also look to develop magnets for things like MRI scanners. So there are a number of examples where investors can also get their money back through the spin outs that we very careful. Throughout this journey, we want there to be economic value on the journey, not just in the event that we get hit the big prize at the end. So I think some of the most successful private fusion companies have recognized that and offer investors the chance to get the big to win the big bet in terms of actually delivering a fusion power plant, or indeed a key fusion system that all the fusion power plants are going to need, as well as making returns now as they spin out some of the technology and into adjacent sectors. So I think that's kind of that's how we see this working when it comes to attracting investors into this space.
Incredible. And perhaps again, for the layperson trying to visualize this fusion process, for us, we can see you in what looks like a standard office with a bookshelf and a few screens at the back, but with obviously some really high-profile scientific calculations happening on those screens. But talk us through, if you can just describe what that fusion plant would look like. And I'll give you an example with an offshore wind farm. We see the wind turbines, and we then see the substation, and we know there are cables that connect the electricity that's generated from the wind turbine to the substation, ultimately to our homes and offices. So when a fusion reactor is finally built and operational, Give us a sense of a description of what we could envisage.
Yeah, I mean, if you were to drive past a fusion power plant in 50 years' time, say, and it was sort of merrily working away, producing this lovely, clean electricity, it wouldn't look too different to a um, conventional nuclear power plant or even a sort of a gas plant. You know, you'd see lots of built infrastructure and some cooling towers because there's a lot of heat rejection involved. The only difference to a normal sort of power station that you would look at is that if you were to go and open the sort of the main building where the actual heat was being produced, instead of seeing a sort of a coal furnace or a gas or a gas burner or a fission core, you would see one of these, well, in our minds, one of these sort of tokamaks, one of these metal donuts, just with the very hot gas just sitting there churning out power in the form of neutrons. So it would look most like a conventional power station, just with a different technology right in the middle of it, producing the power. That's probably the best description I can give.
I think that's really helpful, just because it sets the mind for those of us who would be possibly living next to one of these fusion power plants to get a sense of what we could expect in our backyard, and perhaps feel comfortable that it's going to be there.
Yeah, it's very it's very high density. So just like a conventional nuclear power station, you can get gigawatts out of a relatively low land use, unlike renewables where you need much areas, whether it's for your turbines or your solar panels. So again, you don't need to use up much land to get an enormous amount of power from a fusion power plant. And as I said earlier, it's intrinsically safe. Whilst clearly there are industrial hazards, there are hazards you need to manage, like you do on any power plant. You can be reassured that the actual where the fusion is happening, if there's any problems, it just stops. So I would have absolutely no issue living right next door to a fusion power plant from a sort of safety perspective, and they can be put on small amounts of land, relatively sort of remotely if necessary. So it's a good option in terms of land use for sure.
Okay, incredible. And in terms perhaps the quantum of energy that's going to be provided or produced. So are we talking about 100 megawatt power plant or a 1 gigawatt power plant that's going to be an average fusion facility?
Yeah, I mean, it depends who you ask, really. As I sort of mentioned earlier, there are lots of different ideas, different concepts, and some of those will need to be at quite a big scale for them to work effectively and efficiently, and some of them may be able to be a bit smaller. The kind of technology that we're thinking about and experimenting with behind me, you're talking similar amounts of power output to a typical gas-fired power station. So 1 to 2 gigawatts we would expect it to produce from the kind of the first power plants. But I don't have a crystal ball. That could change. It could be bigger. It could be smaller. But in terms of thinking about the economics and the capital you need to raise, and the technology itself, that's where we think it's going to be at the moment. Fusion it's hard to miniaturize. It's hard to do small fusion reactors that might fit on the back of a truck or something. The physics gets easier. It gets easier to get the conditions you want for fusion and to hold them there and sustain them there if you build them slightly bigger. So we think it'll be somewhere in the sort of the gigawatt range, 1 to 2 gigawatts. And that would mean it'd be very similar to the typical power stations we have dotted around the UK these days.
Okay, fantastic. That's really helpful. So that sets our tone for the fusion power plant. So we will be looking at 1 gigawatt type facilities, complemented by fission, possibly by other renewable energy and low carbon sources. That is the ambition for the energy mix. Incredible. So then obviously the last question, and we briefly touched upon the bankability of this section, is, Joe, if I asked you, is fusion power a bankable investment for investors and lenders?
I mean, I'm a lowly engineer. I'm not an investor myself, so I can only go on the kind of evidence that I'm seeing and the significant increase in private in investment that's coming in to the market. And as a colleague always says, the people with the money are often the smartest people in the room, right? The reason they've got the money is they're very good at assessing risk and understanding where there is potential. So if the investment community is ramping up the amount of money that's going into fusion through their due diligence processes, one can only assume that we're giving out the fusion community is giving answers that they are accepting, and we're displaying a level of maturity and a level of promise that we're actually going to get there that is satisfactory. So, sorry, a long answer. Do I think it's bankable? Yes, because the evidence in the marketplace is telling me it is. So I would certainly encourage anybody who is interested in this to get in touch and with either our laboratory or the many other organizations and find out a little bit more, because I think you'll find that there's some very promising investment opportunities out there at the moment.
Without the shadow of a doubt, you're being far too modest, Joe, because there's a lot of brains sitting on that shoulder of yours. And investors are certainly counting on that tech and the science that sits behind the technology to make sure that the investors and lenders, and then obviously from a financing consultancy perspective, we want to make sure that the technical prowess is sufficiently backed up. So without a doubt, that's been really helpful. So Joe, it just leaves me time to just say thank you for being here. Thank you for bringing insights in what the world of fusion energy is currently and where it could play a role in the energy mix. And we look forward to hearing more and following you on that journey from a technical and a financing perspective too. Thank you, Joe.
Thank you. Thank you very much for having me.
Brilliant. Thank you for listening to Bankable. For early access to energy transition pioneers and to learn how to structure the investment solutions described in this episode and throughout the series, subscribe to the podcast and get in contact at frescocleantech.solutions.